Hi everyone, thank you for coming. This is my fourth or fifth DotNext, I think. It's really great to be here. And this time with a talk that's slightly less technical. So it's still technical, I can't do anything else, but it's not as hardcore as other things because I wanted it to be relevant to as many people as I could. So this is the Performance Investigator's Field Guide. And before we start, I just introduce myself. My name is Sasha. I work for an Israeli training and consulting company called Sela. And if you have anything at all you'd like to talk about, please feel free to catch me later in the discussion zone or on Twitter if you prefer. So the plan for today, I want to tell you a little about my process for doing performance investigations, the strategy, the specific tactics, some of the things I see in our future when we do performance investigations. And specifically, 4 things I would like you to take away from this talk are the process of a performance investigation, what the steps are, at least for me, some methods for doing it right, and some anti-methods for doing it wrong, so you can avoid the wrong things I've learned from experience, a little about tools. Even though, again, it's not a demo full talk, I still want to talk about some tools I use, and importantly, how to avoid getting lied to by the tools, how to make sure the tools are telling you the truth and you're making the right decisions based on their information. So I'll start with the structure of a performance investigation, sort of the way it should work if people let you do it right, if the customer lets you do it right. So the first thing is to obtain the problem description, which sounds easier than it is, and I'll show you some examples of really bad problem descriptions. Next, you want to understand the system, what you're dealing with, what I'm dealing with, sort of which building blocks are there, which parts can possibly have the problem. You run a quick performance checklist to see, like, is this thing even working? Is that thing overloaded? So we'll talk a little about this sort of performance checklists and how they might work. And then hopefully you're able to understand which part is the problem. You don't know what the problem is, but you at least know which part, so you can sort of make progress. This is where you spend most of your time investigating, trying to figure it out. Hopefully you find the issue. Hopefully you fix the issue. Hopefully you verify that you have fixed the issue and that now the system is working right. And here's the most important part. You do a postmortem, so you know what happened, so you know what you did, so you know which tools worked and which tools didn't, and so you can avoid that problem next time around. So this is like a general process. It's used by developers, it can be used by system administrators, it can be used by ops people. It's the general things you have to do. I hope no one's going to argue that these things are important. So let's start with the problem descriptions. Here's an example of something I get once in a while. So the application feels slow. Users don't really know what's slow, but it's slow. Please take a look and help resolve the problem. This is not very useful for me anyway. Or another variation of the same thing, we have a 2-day budget to bring you in. Come in and, find performance problems and fix them. We can try, but it's not very specific and probably not going to be a very good use of the 2-day budget that you have. Something slightly better, and this can be an email from an automated monitoring system, something like this. So since 4 in the morning, one of your specific applications, an ASP.NET application, has its latency percentile increased to 1400 milliseconds from the usual 60 milliseconds. So something is clearly bad, and this is happening across all geographies, so it's not like one specific area or client. And we have tried auto-scaling the system, and that failed. please diagnose. This could be an automated email, or this could be a person writing me something like this, but this is actionable. I know where to look. I know what the symptom is, so I know what would be considered a resolution. If I bring back the latency to 60 milliseconds, they will be happy. So that's sort of more useful. Another example from a non-web application. So this, suppose you have some kind of app used by doctors and hospitals. Clicking from the patient details to the CT screen takes 11 seconds in certain specific sites. This is unacceptable. It has to be under 2 seconds. Please help urgently come in. Again, it's specific. It might even tell you which hospitals. And again, you know what needs to happen for the customer to be happy. It needs to be under 2 seconds again. Now, this whole process of even figuring out what the client wants, what the requirements are, is a lot harder than it may seem. So here's a chat-like simulation. I might ask, what are your latency requirements? The customer might say, we need an average response time of 20 milliseconds, which is really fast for some things, for some systems. And then I'm like, okay, but what are the worst case requirements? We don't have worst case requirements yet. So some requests can take more than 5 minutes, and that would be okay if you have no worst case requirements. No, of course not. Nothing can be worse than 100 milliseconds. This is the worst case. But this is still a little fast for me. But what if it's just 2 requests per day? Can they still not be more than 100 milliseconds? Just 2 requests per day. Okay, fine. Nothing worse than 2 seconds. That's the absolute worst case. And generally, we want 20 milliseconds as the average. But how often is a 500 millisecond response acceptable? You're still not giving me the distribution. Because if you want a 20 millisecond average, here's one way you can get it. You have 96% of requests complete in 1 millisecond, and you have 4% complete in 500 milliseconds. This is still a 20 millisecond average, even though 500 milliseconds looks bad. It doesn't usually end well. So this is what I'm talking about. You want to have some sort of definition somewhere of what acceptable performance metrics are for your system. So you want this many requests to complete under 50 milliseconds, 200 milliseconds, 600 milliseconds, and the worst case has to be, say, 2 seconds, and 99% of requests should complete under 600 milliseconds. Something like this would help you first monitor the system to see if you're meeting these requirements, and second, it will help you fix these issues. It will help you bring the system back to a healthy state. Now, these numbers, of course, they don't appear out of a chat room conversation. They appear out of business goals. You know what your users need. You know what your users expect. You know what your users will not be able to live with. So if your hospital app takes 15 seconds to move from one screen to another, the doctor is going to give up and go drink coffee, and that's going to be very bad for productivity. So you should derive these things from your business goals. And then once you have those metrics, you should have some kind of system in place for monitoring them, hopefully monitoring them automatically and getting alerts if you are not where you should be. And again, these alerts should not just be on the average value, because the average value, we'll talk about this more later, the average value is completely uninteresting. What you want to look at is this sort of distribution of latencies, distributions of your application performance. So once we have that, let's talk about investigating the issue, investigating the problem. And I want to start with some anti-methods before we move to the better way of doing things. So there's 5 bad ways you can try before you get to the right thing. Make assumptions is a bad thing to do, and I'll share with you a story coming up. Trusting your instincts is a pretty bad thing to do when you're dealing with performance, especially in complex systems. Looking under the streetlight, by which I mean you know, there's a street light pointing to a certain place and you can see nothing else but this particular spot. So you look there and you keep trying and you keep looking even though it's just this one spot that you happen to have a light on. Using random tools, because you bought a tool, you paid money for it, so let's run the tool, see what it says. And blaming the tools, so not believing the tools, and again, this comes back to trusting your instincts. The tool doesn't know what it's doing. I know it can't be true. So I want to share with you a failure before we talk about some successes also, how I failed to diagnose a particular issue. So I had a customer with a document management system where clients can access documents, load them, save them, that sort of boring enterprise thing that a lot of us are building. And they reported that certain operations, loading and saving documents, would cause a timeout. I'm simplifying a little, but that's the general story. And the architecture had a network storage appliance, a NetApp appliance, which had all the documents stored on it, and the application server was accessing that NetApp storage appliance. So I wanted to investigate, get some initial numbers from the network side, from the storage side, from the application side. This is the general architecture, very simplified. Clients accessing an application server over WCF, and the application server is just going and talking to that NetApp storage appliance like a network share through, you know, SMB. So I had the tools to monitor WCF. I had the tools to monitor my application server. I had the tools to look at the network traffic, like, you know, a network sniffer. I didn't have access to the actual NetApp box, as I'm sure a lot of you don't have in your own environment, because NetApp is this crazy, complicated thing which only NetApp administrators are allowed to access. So they didn't let me touch that server. Okay, so, you know, I did some analysis and I sent back an email. After looking at 24 hours of network traces, I can tell you that the average latency to the storage thing, to the storage box, was 11 milliseconds, which is really, really fast, but the maximum values I saw were like over a second, which could maybe explain the timeouts. So can you look at the storage appliance, can you look at the network side on the storage appliance to tell me what's going on there? So the customer had a network engineer come back to me and say that the network is not at fault here. The worst case network latency he was able to capture was 10 milliseconds. And this is a local area network. There's maybe one switch in the middle, so it's not very surprising that, you know, passing the packets over the network wasn't really the problem. Everything was pointing to that NetApp box. But also, I got this information. The NetApp consultant is going to come in next week. This is the earliest slot we have for that guy. And in any case, it's very unlikely that the storage is the problem because we have a local NetApp administrator, and he said the storage takes 5 microseconds to process any request, which is pretty impressive. A little later, I got back another email saying it's not really 5 milliseconds, it's not 5 microseconds, it's 5 milliseconds, which is almost the same thing, but it's still clearly not the storage. So the NetApp consultant was able to verify 5 milliseconds is the time the NetApp appliance takes. Except what is this 5 millisecond number? Is it the average? Is it the worst case? Is it the 99th percentile? Here's the kicker. He says it's the maximum average value over 60-second intervals. You can laugh, I don't know what it means. I guess you don't know either. What is a maximum average value over 60-second intervals? I honestly still don't know. So it could be like, you know, he took the average every second, and then he took the maximum of the averages, or maybe he took the maximum every second, and he did an average of the maximums, or something else. I don't know. This is where the NetApp consultant went home. And then I looked online, and I found some performance counters for NetApp. I actually looked at the NetApp documentation. I will never forget this. And I found that NetApp actually has some performance counters you can get out if you have a shell connected to the NetApp box, but they are per second averages. At least not 60 seconds, right? So I asked, can we get these numbers at least, like the per second averages? Unfortunately, they didn't have the budget for the NetApp consultant to come in again, and I couldn't access the NetApp box. It's way above my skills. So this is where this investigation ended, unfortunately. And also, they talked to the NetApp consultant, and he said there is no way the storage box takes more than 5 milliseconds to return results. So this is a classic case for me anyway, of how a performance investigation should not go. I tried on my side to get as much information as I could and to act on information and not instincts, but it didn't work out so well for the rest of the system. So this was making assumptions and trusting instincts. Let's see a couple of simpler examples of where things can go wrong with using tools. So first, there's this approach where if you bought a tool and paid money for it, you have absolutely to run it in every investigation, because otherwise, where is the return on investment? So, you have a CPU profiler. Let's run a CPU profiler on anything that we suspect is slow. In this case, just an artificial example. Suppose I have a web crawler that downloads web pages periodically. We want to improve its performance, so we run a CPU profiler. Now, a web crawler might be doing some things that are not exactly CPU intensive. If we run the CPU profiler, you could get a result that says console write line is taking 66% of the time. So console write line is slowing down my application. I need to improve the performance of console write line. And if you think about it for a moment, then the web crawler probably is just waiting for network data to come in. It's not actually very high CPU bound, but we don't know that. We just run a CPU profiler that only looks at CPU usage. So this is a classic example of using the wrong tool for the job just because that's a tool you have available. Another example of not exactly understanding which tool to use is this. Suppose you have an application which has a memory leak. You think it has a memory leak because it crashes with an out-of-memory exception, which is pretty convincing. It's very hard to argue if you actually have an out-of-memory exception. But if you look at Task Manager, 10 megabytes of memory in use. So no way this application has a memory leak if it only has 10 megabytes of memory in use. Except again, if you look a little closer at the number Task Manager is actually reporting here, this is the private working set column. And I guess some of you already know what's happening here. First, it's just private memory, so it doesn't include memory shared with other processes, such as assemblies loaded into memory and any other kind of shared memory. And plus, it's just working set, which means it's just physical memory, and it doesn't include anything that might have been paged out to disk. It doesn't include virtual memory that you haven't touched yet, so it's not in physical memory yet. It's basically a useless number if you're trying to figure out exactly how much space your application is using. So Task Manager is great, you just can't trust its results implicitly. But there's also the other side of this. So suppose you know Task Manager is not really good, you run a more sophisticated tool like VMMap. This is a sysinternals tool, very advanced, gives you a very nice report on exactly how much memory your process is using in different categories, like shared memory, non-shared, physical, virtual, whatever you want. Except, I ran it here on a Notepad instance that doesn't have a file loaded, and VMMap says that Notepad here has a total of 2 terabytes of memory in use. which is a little suspicious, I guess. I mean, you can't ignore this. It's weird. So Notepad is using 2 terabytes of memory. This might be a little more mysterious to some of us. So it turns out that recent versions of Windows on 64-bit processes have a security feature called CFG, Control Flow Guard. Some of you may have heard of it. If you have, great. If you haven't, it's also fine, because it's mostly relevant for unmanaged code. But what Control Flow Guard does is it reserves in your address space 2 terabytes for the bookkeeping information this security feature needs. It's not actual memory being used, it's just an address space reservation. But if you look at the total reported by VMMap, it includes that address space reservation. So your process is not really using 2 terabytes of physical memory. It only has an address space reservation of 2 terabytes, which is fine because you have a 128 terabyte address space on 64-bit. But it looks very bad. And so you might say at this point, this tool is broken. I'm not going to use this tool anymore. I'm not going to trust sysinternals again. So again, some of these typical mistakes I've seen a lot, and now that you know what to look for, you will hopefully be able to avoid them. So what do I propose? What kind of methodology do I propose? So it's not really my methodology. It's something that's been used pretty often by performance engineers all over the world. It's a method called USE, Utilization, Saturation, and Errors. You might have heard of it before. I just want to introduce the general concept and then share with you an actual investigation. So what this method is you build a diagram of the system, including any connections between components, and then for each component and for each connection, you want to figure out these 3 things. Utilization, which is how loaded that resource is. Saturation, which basically means if there's any queuing, if you have requests waiting for that resource, for example. And errors, which is, errors, exceptions, checksums, and so on. And then if you see any of the issues with utilization, saturation, or errors, you fix them and then try again until all issues are resolved. This is the process. Here's what USE could look like for hardware resources. So you have processors, you have memory, you have graphics cards, you have hard drives, you have network cards, and all of them can have utilization, saturation, and errors measured. And I'll show you how to do so on Windows in a moment. I have a checklist like that. Same thing can apply for software resources also. So you have a front-end load balancer, and then you have an ASP.NET Web API, and then on your back-end you have Node and WCF, and you have a SQL server, and you have a cache server. All of these have utilization, saturation, and errors that you can measure, and if you see an issue, just fix it. So this is just an organized process that you can follow, and the checklist you build is just these 3 metrics for your own resources. Here's a general example for Windows systems, for hardware resources anyway. So for CPU, for memory, and on the next slide, for network and disk as well. Mostly, you can get this information from using Windows performance counters. So you don't have to work very hard, and you can build a very, very simple checklist based on this, which would let you know in the click of a button if you have utilization, saturation, or errors in any of your resources. And that saves a lot of time guessing and running the wrong tool and not trusting the tool. Once you have a checklist like this, a lot of things are easier. Of course, you still have to investigate the specific issue, but it's still going to be easy once you know what the component is. To automate this process, you can either use Performance Monitor on Windows, for example. You could use TypePerf, which is a command line tool, which would print out a CSV every second of any performance counters you provide. And of course, there's third-party monitoring solutions. For example, if you're running on a cloud, your cloud provider probably has some sort of integrated monitoring tool which would look at CPU utilization, disk utilization, network bandwidth, all the basic metrics, so you can get alerts on this, so you get logs that you can look at later. So this really isn't very hard. It's just something you have to invest a little time in early on. So let me share with you a story. That's not exactly an illustration of USE, but it is a successful performance investigation that sort of worked, which was a long time ago. This is a bug we found in the CLR 2.0 garbage collector. It was a while ago, as you can guess. I think it was 2009. And I'm saying a bug, and it really was a bug. It's not like Sasha thinks something was wrong. It was confirmed as an actual bug. So what happened here is we had a packet processing system, which would take packets and do some basic analysis of headers and contents. And it was a soft real-time system that had to process a lot of data. And we had occasional hiccups. By hiccups, I mean the system would freeze and drop a lot of packets. If you look at the logs, there would be a sudden gap in the middle of the log, like a half-second gap, and then another log message that says, I dropped 10,000 packets. Please, I'm not telling you that the garbage collector can pause your application. This is not where I'm going, because I know a lot of you know this. So no, this isn't exactly the case, just to keep you on your toes. So the customer's engineer ran a checklist and was monitoring CPU usage, memory, a lot of things. And they were able to find an interesting correlation between CPU usage and where the packet losses would occur. This is what it looked like visually, because a visualization is always better in this sort of thing. The red line is CPU usage. The blue line is packets processed per interval. So everything goes well until suddenly there's a drop. CPU usage drops, and packet processing drops almost to zero, but not completely zero. And then CPU usage goes 100%, packet processing drops to zero completely for a short time, and then everything goes back to normal, with a little stuttering still, but basically goes back to normal. So this is what we were seeing, and it looked very suspicious because if this was just a GC pause, then there wouldn't be any packet processing during the GC pause, but this isn't exactly what we were seeing, so it was suspiciously not what, I mean, a lot of us would expect. And here's another funny thing. The actual delay is always close to a multiple of 250 milliseconds. So like 252, 503, 751, always a multiple of 250 milliseconds. Very, very suspicious again, because coincidences like this, they just don't happen. That looks suspicious, I said. It looks like it correlates with garbage collection, but we have such a small heap. And also, it doesn't explain why 250 millisecond multiples all the time. So this was a little harder. I asked and got a stack dump of the threads in the application when this hiccup was happening. You can imagine it's a little harder because to get a stack dump, you need something like a debugger on the system. You have to invoke it at exactly the right moment. So there's a little more trickiness here. And here's sort of what it looked like. So 6 threads, 4 threads on the right look like GC threads, and they're waiting for the garbage collection event to kick in, to tell them that they need to do a collection. So they're not even working yet. And there's 2 application threads. One of these application threads is currently parsing network packets. That's the one on the left. And the one next to it is making a memory allocation and asking the garbage collection, the garbage collector to start. And then the garbage collector is calling a key function called suspend EE, suspend execution engine, which is responsible for stopping the application threads so that the garbage collector threads can start working. So it's not that the GC is working very hard. We're not there yet. We are trying to stop the application so we can start the garbage collection. And this is where we are stuck for 250 milliseconds, 500 milliseconds, 750 milliseconds, which looks really, really weird. So we reversed engineered the suspend EE function in general terms, and we got something like this. Here's what it's doing in pseudocode. While not GC suspension complete, so as long as we haven't successfully suspended all the threads, and not gave up, as long as we haven't given up, do a wait for single object with a 250 millisecond interval. So this is where the 250 is coming from. And this is happening in a loop, okay? So it can happen once, twice, 5 times. And the thing is, the actual suspension would never complete successfully in our case. What would happen is the give up option. So we would occasionally, the GC would give up, and then if it gives up doing the suspension in the normal way, there's another check later that says, okay, if we have given up and we haven't successfully suspended, then just stop the thread. Like with the Windows suspend thread API, which always works. But this is like a violent suspension, very violent. So this looks like a bug. Not the code here, but the fact that the suspension is not actually happening successfully. And I wrote this up, and we reported this. And you may know her, Maoni Stephens, who's the lead engineer working on the .NET garbage collector. She replied to my blog post, and she said, yeah, I looked at your repro, it is an issue, and it was fixed later. So I guess the story here is not that we're so amazing where we're able to find a bug in the GC. We don't really know what the exact bug was. Today, the GC is open source, so I like to think that I might have been able to actually find the problem on the source code level. But back then, you know, we were looking at assembly in IDA Pro and trying to reverse engineer what's happening. And we got this result by careful monitoring, by looking at logs, by looking at CPU utilization graphs, nothing particularly fancy. And it wasn't easy. It took weeks to get there. So I'm not sharing this as a, wow, we're so great story. I'm sharing this as a lot of hard work based on facts eventually leads to interesting results. So let's talk about tools for a second, about good performance tools. There's 3 kinds of tools that I tend to use. If you think about it, most of your performance tools are of one of these 3 kinds. First, you have counting tools. How often is this happening? How many requests, for example, am I getting per second? How many garbage collections do I have per minute? Counting tools. Second kind, latency tools. How much time is this taking? So how much time are my ASP.NET requests taking? Or how much time does it take to move from one WinForm screen to another? And third, you have stack-based tools, which tell you why something is happening, where in your application source code, a certain condition occurs. And in terms of cost, overhead, the counting tools are usually cheapest, the latency tools are a little more expensive, and the stack counting tends to be the most expensive thing because there's more information that you have to process. Now these tools have, for me, 5 important qualities, which might seem obvious, but not so obvious for a lot of tools I use. Low overhead, we'll talk about this in a moment. Accuracy, so you can trust the results you get out of the tool. Quick turnaround, so you can get results without waiting 6 hours for the data to be analyzed. Production readiness, which means you can run this tool on a production system and not just your development box. And I called it focusable here, by which I mean the ability to zoom in on a particular area, on a particular class, on a particular function, and not just look at a lot of raw data. These are the 5 qualities. So let's talk about them briefly. In terms of overhead, hopefully it's obvious that any observation may change the state of your system. But some tools have a very, very small overhead. They're very non-invasive. Some tools actually have a lot of overhead. Hopefully, the tools you use have documentation. Here's a snippet from one of my own tools, which I'll talk about a little later. It has an overhead section on its README page, which says what to expect. If you're doing this, you should expect 5 to 10% CPU overhead. If you're doing this, you should expect literally no overhead at all. A lot of tools don't have that. You don't even know what to expect. It could be a 5% overhead. It could be slower by a factor of 5. And you just don't know because no one ever went to the trouble of documenting it. So if your tools don't have any documentation, you have to test. You have to test your performance tools before you actually use them in production, before you even use them in development, so you know what to expect in terms of overhead. Regarding accuracy, if you happen to be a Java developer, this may sound familiar, otherwise it's a little surprising, but most Java profilers, most of the CPU profilers Java developers use, actually lie to them, or lie to you, all the time. They give you totally irrelevant results. And the reason is, they use a documented API called getAllStackTraces, which gives you a sample of what each thread is doing on the system when you call that getAllStackTraces function. The advantage is it's cross-platform. You can run a profiler that works on Windows, on Linux, on Mac, on any platform that runs Java. The disadvantage is that you get the stack trace, you get the actual stacked sample of your threads only when all the threads are at a safe point. Now, if you don't know what a safe point is, it doesn't matter a lot in this case, but it's the gist is, it's not any instruction the thread is executing. So if you ask for a stack trace, you get the stack trace not from right now, but from some point later when the thread decides it wants to give you its stack trace. The result is you can get totally unrelated results, totally disconnected from reality. Just to show you how disconnected it can be, this is an actual academic paper that evaluated Java profilers. So you can see on the left 4 different profilers telling you what the hottest method was in a particular benchmark. So 2 profilers, the one on the left and the one on the right, agreed it was a method called JJScanToken. The profiler, the second profiler from the left thought it was getPosition from parent. The third profiler from the left thought it was default namesType.evaluate. Totally different methods, totally different numbers, 4 different profilers. And it's not the profiler's fault, essentially. It's the API the profiler uses to get results out of the target process. This can happen with .NET tools as well, although it's less likely. Sort of what do we take from this? You have to sanity test your profilers. If you're using a new tool, you should run a little test that has a mix of CPU work and I/O work, like sleeping or reading stuff from disk. And you should see that the profiler tells you a sensible thing. That the profiler tells you this is where you're spending CPU time, this is where you're spending I/O time, and it doesn't lie to you completely. If it lies to you, it's probably not your fault here, it's the profiler's fault, and so you shouldn't use it. In terms of quick turnaround, what do I mean by that? This wall of text, you don't have to read this whole thing, is from the instructions for profiling .NET Core on Linux, which is a great thing you'll want to do, and there's a talk today about this later. So the instructions begin by, prior to starting the .NET process, you have to configure some environment variable, which is something I personally have a big problem with. But okay, let's suppose you've done that. The instructions end with, take the zip file generated by this whole sequence of steps, copy it over to your Windows machine, and open it there using perfview. And then you'll be able to analyze the recording. This is the workflow. This is the official process. I hope you see how ridiculous this is. You profile on Linux, you copy a zip file over to Windows, and you open it there. Very useful for production debugging and profiling. I sort of built or hacked around an alternative, which is a bunch of scripts that don't really work very well, but at least they let you get results on the Linux box. So you don't have to copy things over to your Windows machine. And the thing you get there at the end is something I want to briefly touch on, just a couple of minutes, because it's something a lot of Windows and .NET developers haven't seen. The visualization you see there is called a flame graph, and it's worth spending a minute on. This is a way to visualize lots of stack traces. For example, where your application is spending CPU time, or where your application is doing lots of disk accesses, or where your application is allocating lots of objects. You have a lot of call stacks, and you want to visualize them in a nice visual way rather than reading a lot of text. So what do you do with the flame graph? Basically, every rectangle you see is a function. The colors are usually just random, so you can ignore the colors. And the y-axis is the stack depth. So if a function called another function, it will be on top of that function and so on. And the wider something is, the more time you spent there. So it's very easy to visually zoom in into the thing you care about. Some examples of specific pieces from this graph, just to give you an idea so you can see some of the text. In the left corner, you can see a thread that is actually suspending other threads for garbage collection. And if you look at the percentages, you see it's 1.3% of my application's execution. If you look on the right, you see a thread that's trying to allocate heap space, and then it's calling a bunch of functions again inside the garbage collector. On the bottom, you see multiple function calls. I'm not going to go through this thing. It's just a way of visualizing stack traces that's very, very useful, and I encourage you to take a look a little later. There are talks online about how flame graphs are super useful, and you should check them out. Next thing is invasiveness. So we talked about some bad things profilers can do. Invasiveness is one of them. I want to touch on this very briefly and then talk about non-invasive tools. So a lot of profilers will be bad for your system's reliability and responsiveness because they are too heavy, right? They do too much stuff in your process. For example, the Visual Studio instrumentation-based profiler actually has to recompile your application and run it with additional probes that measure performance. This isn't something you can do in production, obviously. If you look at the CLR profiling API, which is used by some tools still, even today, it's based on injecting a DLL into the target process, which is something you may be okay with in development. Not sure if you want that in your production system, to inject a new library into a running process. An extreme example, on Linux, there are actually tracing frameworks which are built around a kernel mode driver, a kernel mode module that you have to install on the system in order to use that tracing tool. So you might trust these guys very much, but it's still a little suspicious that to run a tracing or performance tool, you need to load a new thing into your kernel. On Windows, it probably wouldn't fly. On Linux, it's sort of acceptable, but still a lot of people are worried about doing that kind of thing to your system. Windows, fortunately, has a very lightweight, relatively lightweight anyway, tracing framework, which hopefully you've heard about. There were talks about this at DotNext last year and the year before, which is called Event Tracing for Windows. This is a tracing and performance monitoring framework that you can use to do CPU profiling, to figure out where you have garbage collections, to figure out where you have heavy disk accesses, really a variety of different useful things that you can do. However, even though ETW is not very invasive, it has a turnaround problem. Again, by turnaround, I mean you might wait too long to get useful results. Here's an example from a log file generated by PerfView, which is a great tool. I talked about it at last year's DotNext, I think. I collected CPU information, CPU usage information for 10 seconds. The amount of data actually collected was 15 megabytes. Not very good, right? You can't really run this for hours. You'll get lots and lots of data. And then after collecting for 10 seconds, I had a CLR rundown start and last 12 seconds. And then I had a conversion step, whatever that means, take another 4 seconds, and another 4.3 seconds, and another 0.2 seconds. And this is considered relatively fast. that you profile 10 seconds of execution, and then it takes you like half a minute to open the thing, it's considered relatively okay. But it's not something I was really willing to live with. So I want to share with you a couple of my own tools that I wrote because I sort of couldn't live with that. They're both open source on GitHub. One of them is called eTrace, and this is a command line interface to ETW. So you can tell it which events you want, and it will print them out in real time. When the event occurs, it will be printed to the command line. I'll have all the links for you at the end. If you want, you can take screenshots later. So here's what eTrace may look like. You run it, and you tell it, okay, I want GC start events, and whenever a GC starts, I want to print the process, the GC type, the GC reason, and then it prints out for you every time there's a garbage collection on your system, which process it was, which kind of GC it was, and why it was triggered. The example on the bottom is GC allocation ticks, which is basically a way of seeing what kind of objects you are allocating frequently, in simple terms. So this is the sort of thing you can do. You give it a query, if you will, and then it prints out on the command line whenever an event of that type occurs, it prints out the information you asked for. Another thing I wrote a tool for is called live stacks, which is also ETW related. What this does is collect stack traces of interesting events, such as where a garbage collection happened, where I accessed a particular file, where I spent lots of CPU time. And the key difference between live stacks and some other tools is that it can give you results again in real time. You don't have to wait for some post-processing to get immediate call stacks of something that happens. One example, this is the default mode for CPU profiling. Just look at the Visual Studio process and give me the hottest call stack in the Visual Studio process in terms of CPU time. It waits for you to hit Control-C and then immediately prints out the hottest stack in the Visual Studio process, which in this case is partition manager, schedule batch processing, whatever, it's Visual Studio. I don't really know what it's doing. Another example, show me where a garbage collection is triggered, what the call stack was that caused a garbage collection to happen. Again, in a particular process or across the whole system. And it will print out a call stack with where a GC is happening. Again, this is almost real time. And you can use it to generate flame graphs also, to get a visualization of the actual call stacks that were printed to the console previously. So these are a couple of tools. You can use them, you don't have to. I found them useful because they give me quicker turnaround, quicker results without having to wait for post-processing. Next thing I want to talk about very briefly is designing your systems, your production systems for instrumentation. When you build a system, when you build a library, when you design the architecture for your next big thing, here are some things to think about for making it easy for you and for other people to do performance investigations in the future. So you want to make sure call stacks for interesting events are easy to get. For garbage collections, for disk accesses, these are examples from the OS side. But you might have your own interesting events, and you want to make sure it's easy to get stack traces to understand where they are happening in your code. You want to embed static instrumentation, which is often called trace points, so people can attach to your process and get real-time information on certain events happening. Sort of like a log, but a real-time log that you can turn on and off at runtime. And for important events like this, for important messages, it should be easy to turn this on and off without a high overhead, without restarting your system just to tune the log level. And of all these things, you want to have examples and documentations for the aspiring performance investigator. When a performance investigator comes in, they should be able to do this sort of analysis without having to first investigate the way you built your system. This should be documented, and you should have examples of doing these things. Now, I'm going to skip ahead a little. I just want to share that on Windows, for example, when you look at .NET, it has really good instrumentation tools built in. It has ETW events, which I mentioned previously. It makes it possible to grab call stacks of interesting events that happen and resolve them to function names. And it's all, well, it was worked on for more than a decade by a lot of people in a lot of tools. And it's not so easy to build. Because if you look at the same story on Linux today, and again, there's a talk today about .NET Core profiling on Linux, the story isn't so good. And it's not because Linux doesn't have good performance tools. It's because it's not easy to design a platform like .NET Core to be easily profilable and easily debuggable on a new platform. So one example of where this is bad, .NET Core on Linux has events like GC events and disk access events, but you can't get call stacks for these events. You can just know the event has happened, which is a lot less useful. Or for resolving call stacks, for getting actual function names out of a call stack you captured, you have to do a lot of preparation. And this is why the default workflow is to copy the zip file over to Windows and open it there. And this is, I mean, it's a matter of priorities. If you think performance investigations are a key requirement for the system you're building, you will not release something like this. That's just my point of view, anyway. Last thing for us to talk about today is statistics and how tools lie to us. So I'm going to use all the time I have left to share some common errors, some common pitfalls you may run into if you trust your tools, too much, if you trust statistics too much. Some things I've already mentioned before, like averages are basically meaningless, median values are basically meaningless, percentiles and distributions are useful, but you have to be careful. So let's talk about some of these things a little. So suppose someone tells you the average response time of my system is 29 milliseconds. Sounds good. What does it exactly mean is really hard to know, like we already saw in my previous examples. It could mean something like this, where the average is 29, the worst case is like 50 or 60, and the best case is close to 0, so a nice normal distribution around 29. Or it could mean something like this, where most of the data is on the left, like 10 milliseconds response times, but there's also a mode, a clear mode of much slower results, up to 250 milliseconds, which is still giving us an average of 29. The only way to actually get a trustable number is by not looking at the number, is by looking at the actual distribution. This is a really nice article I saw online. The dinosaur was there for a reason. I'm going to go back for a second here. All these point distributions, they have the same average, they have the same standard deviation, and they have the same cross-correlation. So if you just look at the numbers, it basically doesn't mean anything. You don't know the shape of your data from looking at the numbers. Now, I don't want to pick on anyone here, but this is from a very popular library that I love and use every day, well, almost every day, called benchmark.net, which I'm sure a lot of you have used and heard about. It is great and it's awesome, but it doesn't show you the data. At least, well, by default, when you run it in the default console mode, it prints out a lot of numbers. It prints out the averages, it prints out the standard deviation, it prints out confidence intervals, it prints out quartiles. It doesn't show you the shape of your data, unfortunately, at least again by default. And this is important. For some kinds of work, for some kinds of investigations, not seeing the shape of the data means you're going to miss important things. So here's an example of important things you could miss. Suppose this is my latency response time of my system. Again, the 99th percentile even looks pretty okay. My 99th percentile is like 170 milliseconds. So 99% of my requests complete pretty quickly. But there are hiccups. Some results are much worse than that. My hiccups go all the way up to even 1,000 milliseconds. And in a lot of cases, what you actually investigate is the hiccups, is the worst cases, is the things that user report and will ask you to look at, which are not around the average values. The only way to visualize this right is by either plotting everything, like these graphs you see here, where you see every single data point, or by plotting distributions. By plotting the 99th percentile, the 99.9, the 99.999, all the way up to the worst case, and then trying to visualize like where am I falling, is this reasonable that 99.99 has this latency? Another common fallacy, another common mistake people do with percentiles, people make with percentiles, is trying to do mathematical operations on percentiles. So here's a customer report. I'm happy to report over the last 24 hours, the average 90th percentile across all my machines was 57 milliseconds. You should have stopped in the beginning of the sentence when they said the average percentile, because you can't average percentiles. Suppose you have two servers. This is the distribution. The 90th percentile on the left server is 92 milliseconds. The 90th percentile on the right server is 22 milliseconds. The numbers don't really matter, but you can't average them together. Because the 90th percentile of all your requests in this particular simulation is actually 68, and not 57, which is the average of 92 and 22. So you can't average these numbers, you can't average quartiles, you can't average percentages. You have to actually look at the distribution, you have to look at the underlying data, and only then you can report something at the data center level or the multiple machine level. You can't average these numbers. And one final thing about percentiles, you may ask, like, who cares about the 99th percentile or the 99.99th percentile? None of my users are even seeing this. So here's the Amazon.com page, advertising Echo Dot or whatever, and that page made 328 requests. Now, assuming all the requests are independent, what is the probability that at least one of them was in the 99th percentile? And the answer is 96%. So it is very, very likely, if, again, assuming that all requests are independent, it's very likely that if you go to Amazon.com, you will hit at least one request in the 99th percentile. And if your users are accessing a system that is comparably complicated, like Amazon's, then you will hit the 99th percentile very often also. So each user on each interaction may be hitting these worst cases, which seem like worst cases, but they really aren't the worst thing that can happen. Okay, last thing I want to mention, just very briefly, this could be another talk in and of itself, is that large systems, where you have more than 1, 2, or 5 machines, need large tools. Tools designed for cluster scale, tools designed for cloud scale, which at the same time still give you the ability to focus in, to drill in, and get the information you need about a specific user, about a specific request, about a specific machine. A lot of tools are available. Generally, these are called application performance monitoring tools or application performance monitoring frameworks. Just a couple of example screenshots. This is from an open source tool by Netflix called Vector. It shows you a dashboard, but you can still zoom in. You can click on a particular instance, and then you can say, show me a CPU flame graph for that instance, or show me disk utilization for that instance. So that ability to drill in is important. Or this is a screenshot from New Relic, an APM tool which works with .NET also. It shows you requests across your system and where you're spending time servicing these requests. And if you want, you can zoom into a particular request. You can zoom into a particular user's session. So wrapping up, after you've done a performance investigation, the most important thing you shouldn't forget is to sit down and actually document what you did. Document the process, document your findings, document the tools you used and the things that didn't work. And I mean, for me, the most important reason I'm doing that is that I don't have to repeat my mistakes, is that I can save time on my next performance investigation. But obviously for you, it could be for others people benefit as well, for your team, for your organization, so you know what works and which practices work. And hopefully the next time around, this is gonna be automatic. You don't have to bring in a person to do this investigation if you can build an automatic diagnosing workflow around that tool. So in summary, hopefully we've talked about the process for a performance investigation, what it looks like, what works, what doesn't, what anti-patterns you should hopefully try and avoid, or at least recognize if you see other people fall into that trap. We talked briefly about statistics and how tools can lie to you, and also which tools you should trust and what the qualities of good performance tools are. I have a references slide here, but you don't have to take a screenshot of it. It's better if you take a screenshot of this slide, which has a link to the presentation and everything I talked about. And if you would like to stay in touch, I'll be in the discussion area, of course, after this talk. And I'll also be very happy if you reach out on Twitter, on GitHub, by email, any way you prefer. I hope you enjoy the second day of DotNext. Thank you very, very much for coming. I hope to see you again. Thank you.